1-1, variables and expressions. So our objective for this section is to write algebraic expressions. And what you should know by the time we're done, that's the essential understanding, is that algebra uses symbols to represent quantities that are unknown or that vary. You can represent mathematical phrases in real-world relationships using symbols and operations. So basically what we're going to do in this section is we're going to change words into math, and we're going to learn how to represent different sort of expressions with math and vice versa. So the first thing we're going to talk about is a mathematical quantity. Okay, so a mathematical quantity is anything that can be measured and counted. Think of anything, the number of people in the class when you're sitting in your normal math class. Those can be measured, those can be counted. Easily count them up. Some quantities remain constant, and others change or vary. And these that vary are called variable quantities because they vary, they change. So our variables are symbols, usually a letter, usually X, but doesn't have to be. It can be any letter you want. Could be any symbol you want. Really, X has become sort of the default for when we use a variable, but that can be anything we want. So a variable, usually a letter, and it represents the value of a variable quantity, right? Something that could change. So we have two types of expressions. The first is an algebraic expression, which is a mathematical phrase that includes one or more variables. And the second is a numerical expression. This is a mathematical phrase involving numbers and operations, but no operation symbols, but no variables. So an algebraic expression would be something like 2x plus 3. It's got an operation, it's got the variable x, okay, and it's got some other numbers going on there. A numerical expression would be something like 2 plus 3 is equal to 5. That has no variables. None of those numbers ever change, right? It's just a numerical expression. It can have the operation symbol like the plus, but no variables. So now we got some definitions out of the way. Let's try to write expressions using addition and subtraction. So what we're going to do is we're going to write an algebraic expression for the word or phrase. So look at the first one, A. 32 more than number n. Well, what's going on here? So we're starting at some number n, and we're trying to get 32 more than that. So let's write that down. We started at number n, and we want 32 more, which means we want my quantity to go up, so we are going to add to it. Okay? So when we see more than, right, it doesn't necessarily mean like greater than or less than. It's not that kind of expression. So what we're going to do is we're just going to take some starting point and go more, or like in the next example, less. There's a couple different ways you can do this. We can use, whoops, we can use plus. We can use the word sum. Okay, both of those mean that we're going to use the addition operation. Okay, so our next example says 58 less than a number. So when we we're going to, now here's the trick. We're going to start at a number, and we're going to do 58 less than that, which means that we are going to subtract. Okay, so again, there's a couple other ways that we can represent that. We can say the word subtract. Okay, we can also use the difference. One thing you have to be aware of here is that we're taking 58 less than a number n. So that's where we're starting. This expression right here is not going to be the same as that. The way we would read this expression is going to be n less than 58. Okay, so that is something that we definitely want to be careful with. Okay, so at the end of each example, we'll try a little got it problem. Okay, so these are going to be very similar, and we'll go through these fairly quickly. 18 more than a number n, again, just like part A, we're just going to start with a number n and add 18. Next, let's try writing expressions with multiplication and division. So now we're going to write an algebraic expression for the word phrase, and we're going to have 8 times the number n. Just some notation to look at here. Well, we know we want multiplication, right? That's what times means. That's going to be multiplication. So we could do this. Okay? But there's a problem with that. Is that symbol right there, the x, I don't want to use that for multiplication anymore. Okay, I want to try to get away from that, especially as we progress through algebra 1 now, algebra 2 later. You're gonna want to try to not represent multiplication using an x because it can get confusing because that could be a variable. So our better way to do it is going to be by 8 with a dot n. That's a pretty standard convention. And 8 with a parentheses n, or nice and simple, when we have a variable and a number, we can just write them right next to each other. 8 times n. Okay? Other ways to say the word times is multiplied, or we can say the product. Okay? Part B, the quotient of a number n and 5. So now, quotient, we're going to be talking about division. Okay? So we can say n divided by 5. But again, that symbol can be a little bit confusing when we're writing a long expression. Okay? Best to write that using what this symbol represents. Notice how the division symbol has a dot above and below a line. Well, those dots represent the first thing and the second thing right there. So the better way to represent division, so let's get rid of this, is n over 5, okay? With the n on the top and the 5 on the bottom, which means n divided by 5, or over 5. We can say it like that, however you want to say it. The one that everybody kind of forgets, though, is quotient, which is in the problem. Let's look at our got it problem. A couple different ones down here. So what is the algebraic expression for each word or phrase in parts A and B? 6 times the number n, going to be 6n. The quotient of 18 and the number n. Now this one is slightly different than the one before because now we're going to put 18 on top. So you got to be careful when we're dealing with quotients, is that's the first thing, that's the second thing. Okay? And that's something that we can look at right here in the third one, in the reasoning part. Do the phrases 6 less than a number y, 6 less a number y, and 6 less than a number y mean the same thing? And in fact, they don't. So if we look at the first expression right there, 6 less a number y, which means we're going to start at 6, and we're going to go down by some number y. As opposed to the second expression right there, which is 6 less than a number y, which means that we're starting at y and getting 6 less than that. So definitely two different ways to express similar, but not the same expressions. Okay. So let's make it a little more complicated here and write expressions with two operations. So now we got to have two things going on. So here's our first thing, 3 more than twice the number x. Okay, so 3 more than means that we're going to add something, and twice the number x, that means that we're going to make something twice as big. And the way we make something twice as big, multiply it by 2. So we're going to take 3 plus 2x. Now, we could have written it the other way. With addition, it doesn't really matter. Usually, the better way would be with the variables first. But we'll get to that more later. Okay? 9 less than the quotient of 6 and a number x. Now, when we're talking about subtraction, Order is very important, and we can't just switch them up either way. So 9 less than, that means that we're going to subtract something, the quotient of 6 and a number x. So we're going to start, ooh, we're going to start with my quotient, which is going to be 6 over x, and I want to get 9 less than that. So there's my expression. The product of 4 and the sum of a number x and 7. So product means I'm going to multiply this thing and that thing. Okay? So my first thing is 4. I'm going to multiply, so I'm going to use parentheses. And now I'm going to multiply a sum. So now I'm going to be adding two things together. Okay? So the sum of a number x and 7 is x plus 7. Let's look at my got it problems. Whoops. And what is the algebraic expression for each word or phrase? 8 less than, so that's subtraction, the product of a number, x and 4. So that's 4x minus 8. 8 less than the product of a number x and 4. Twice the sum of a number x and 8. So we're going to multiply by 2. And the thing I'm multiplying by 2 is my sum. And the last one, the quotient of 5, that goes on top. And the sum goes on the bottom. And there's my quotient of 5 and the sum of 12 and a number x. Okay, so in problems 1, 2, and 3, we were given word phrases and we wrote algebraic expressions. We can do this the other way. We can go backwards. So we can translate algebraic expressions into words. So problem 4 is using words for an expression. What word phrase can you use to represent the algebraic expression? That, 3x. Okay, so what exactly happening there is it's going to be 3 times a number x. That's one way to do it. Another way to do it is the product of 3 and a number x. So two different sentences, both means the same thing. Let's look at a few more. So for my got it problems, I don't have a lot of room, but what word or phrase can we use to represent these expressions? So we could say x plus 8.1. We could say the sum of x and 8.1. Doesn't matter if they're decimals, we're still going to say the same thing. So that's part A. Part B, that one right there. Now we have two things going on. So now we have to have a product and a sum. So we're going to say, well, let's do it an easy way first. Let's say 9 more than the product of 10 and a number x, or just 10 and, oh, let's say it nice. 10 and a number x. Okay. Or we can say that as the sum of, so I'm going to add two things together. What are they? Sum of the product of 10 and a and a number x and 9. So if you look carefully there, I said the sum of two things, this and that. Okay? So part C is going to say the quotient of n over 3. So the quotient of n and 3. Or we can say n divided by 3 or n over 3, but the best way is quotient. And the last one, D, is going to be, again, two things going on there, so we have to be very careful in the way we say it. And we can easily say 5 times x minus 1, but we want to be a little bit more clear, and so we can say the difference of the product of 5 and x and 1. That can be a little confusing though, since we got so much going on there. Okay, the little bit better way to do it is maybe 1 less than the product. Let's even make this simpler. 1 less than 5 times x. Nice and simple. So let's finish this up with seeing how we can use words or algebraic expressions to write mathematical rules that describe some sort of real-life pattern in this word problem. So problem 5, we're going to write a rule to describe some sort of pattern. So the table below shows how the height above the floor of a house of cards depends on the number of levels. So look at the picture over here on the right, and we can see that my table starts at the floor and is 24 inches high. Then each row of cards is going to be 3.5 inches tall, okay? Which means that by the time I get to the top, I'm going to be much higher than where I started, obviously. So if I look at the table, okay, if I look at this table right here at the second level, I have the height of the table, 24 inches, and then 3.5, one row of cards, times 2, because I want the second level. So that's going to be one row of cards. It's going to be up to right there. The next one, number 3, would be up to right there. So now we're going to have 1, 2, 3 rows of cards, and then the same thing for the fourth one. To write the nth row, we're going to need to know numerical expressions for the height of all the different levels, and we're going to need to look for a pattern. And I think we can all see it already, is that each time we're going to multiply by one more row. So we're always going to have 3.5. We're always going to have 24, but right now we're going to get one more row. So let's do it first with words and then as an algebraic expression. Okay, so words, when we describe what we're doing, we're going to multiply the number of levels, number of levels by 3.5 and add 24. Okay. So that's a little description of what we're doing with words. To make an algebraic expression, we do 3.5 times the number of levels and add 24. And now I have my algebraic expression for what's going on with this table with cards. Okay. So next, a group of students built another house of cards that has 10 levels. Each card 4 inches tall, and the height from the floor to the top of the house of cards was 70 inches. How tall would the house of cards be if they built an 11th level. Okay, well now my formula is the things that are going on a little differently, okay? But I'm starting now at 10 levels at 70 inches. So if each card was 4 inches tall, to build an 11th level, I just have to go up another 4 inches. So it's going to be the start plus another 4 inches to be 74 inches. And another group of students built a third house with n levels. And each card was 5 inches tall now. And the height from the floor to the top of the house of cards was 34 plus 5n inches. And if they're going to put one more, then again, we just need 5 more inches. Okay, so that's going to be 34 plus 5n plus another 5. And then, of course, hopefully you can see that those two, since they're just numbers, are like terms, something we'll talk about more later. So that gives me 39 plus 5n. Okay, to our got it problem down here, suppose you draw a segment from any one vertex of a regular polygon to the other vertices. A sample for a regular hexagon is shown below in the green. Use the table to find a pattern. So, okay, let's see what the pattern is. So we have 4. The number of triangles would be 4 minus 2. At 5, we have 5 minus 2 triangles. So this is going to be 2. This is going to be 3. This is going to be 4. Okay? And I can see 1, 2, 3, 4. 4 triangles. Okay? So for n, we're simply going to go n minus 2. And that would be the number of problems of triangles formed by a regular polygon. So that's my expression. In words, it's very simple. 2 less than n, or n minus 2. Okay. That brings us to the end of 1-1 variables and expressions.